Start with the first slide. The first thing we're going to do is we're going to factor each of these inequalities as if they're equations. Again, factor them the same way as if they were equations. Get everything over to one side, make 0 on the other side, and then factor and solve the same way you would do it as if it were an equation. Now, instead of calling those answers solutions, we're going to call them what are called critical points. If you want to highlight that, you can. Here we're going to call them critical points. That's the idea here. They're not going to be answers. In the quiz you just took, you got answers for each of the equations because they were answers. They were single point answers. Now we're going to look at solution sets, a range of values. So we need to identify these things called critical points. What the critical points do is they act as boundaries. Okay, each of these act as a boundary. And the boundary can limit the solution that you're going to get as an answer. And we're going to mark them on a number line. We're going to mark the critical points on a number line, and they're going to create boundaries, and as a result, you'll have several regions that you can test. We're going to test those regions with points, similar to the way we tested when we solved inequalities graphically, and then mark each region as positive or negative. So it seems like a lot of steps right here, but let me run through an example with you using these steps, and you'll see that it's actually pretty straightforward. So let's take a look at this first example here. Imagine that it's an equation first. If this were an equation, I would think of it as follows. I would think of it as y squared minus 3y equals 0. That's what it would look like if it were an equation, right? Now, is everything on one side of the equation? What's missing in this case, though? Just out of curiosity, what term is missing? You've got a squared term, you've got a linear term. The constant. There's no constant here. Oh my God, there's no constant. I can't factor. No, that's not true. What can you factor? George? Very good. So as George mentioned, we could take out a GCF. The GCF is y. Now, if this were an equation, what would you get on the next line? What would you say? Tristan, what would the next line read if this were an equation?
If this were an equation, would you move the y over or no? No, oh, wait.
What does y minus 3 become as an answer if it's an equation?
Y equals 3.
And over here?
The y equals 0.
All right, so if it were an equation, that's what you would have. Agreed? You should know this at this point. Once you factor, you set each factor individually equal to 0. So setting this one equal to 0, right? Y minus 3 equals 0. That's what gives you y equals 3. Now, these are no longer your answers, though. These are called critical points. I don't know if I came up with that name or if I read it somewhere. I forget, to be completely honest. But I call them critical points. Now, the reason that they are critical is because they create boundaries. They create boundaries on your number line. So now that we remember, oh wait, this is an inequality, wasn't it? So let's go ahead and draw a number line at the bottom now. And let's identify our critical points on the number line. Now, think of 0 and 3 as boundaries. How many regions are there if I think of these as boundaries? How many regions are there on the number line now? If I have two boundaries, how many regions? 3. The first region is right here. The second region is right here. And the third region is right here. So far, so good? I can't see you, Bridge, so I need just eye contact. Good? Yeah? I just want to make sure you understand. So that's why I'm before. Now, once I know that I've got 3 regions, I need to go back and test a point in those regions. So what point is easy to test over here? -1. It makes the most sense to test it there, right? Now, fun fact. Usually you test things in the original. This is the one time I'm going to tell you, test it in the factored form. It makes life a lot easier. In the original, later on, you're going to see why it's hard. Right now, it really doesn't make much of a difference, but it makes it a lot easier. So plug in -1 here. It makes this number negative. I don't care what the number is, but it's negative. Yeah, it's -1 times whatever this is. What's -1 minus 3? Negative 4. So you have negative times a negative, which gives you? So let's mark this region as positive. I don't care what the number is. I'm just marking it as positive. I know it sounds weird. I'll show you in a minute why this works. Okay, now test the point in the middle region. What point works in the middle region? I would definitely test 1 here. You could test 1 or 2. Either one. I would test 1. Plug a 1 in right here. It's positive. Plug a 1 in right here. What's 1 minus 3? Negative 2. So you have a positive times a negative. Positive times a negative. This region could be identified as negative then. I hope we're all focusing. I'm seeing people looking at other stuff as if you're doing other things on iPads. I really hope we're all focused. Region 3. I pick a point in the third region. What's the point to the right of the number 3 that's the easiest to choose? 4. Plug a 4 in here and here. You get a positive when you plug a 4 in here. When you plug a 4 in here, do you get a positive again?
Yeah.
You sure do. Positive times positive gives you. Okay, so that's our regions. Now, look back at the original inequality. This says, when is the function negative? That's how I read this. Again, look up please. This tells me, when is the function less than or equal to 0? It's really saying, when is it negative? Or 0, obviously. But when is it negative, right? Which region was negative? 0 to 3 was negative, right? So that region automatically gets shaded. Shade that middle region. Now, it says less than or equal to. So on the critical points, I could put open circles, but because it says less than or equal to, I put closed circles. So this answer is the following. Okay? That's in set notation. In interval notation, we'd have the following. What would we have in interval notation? How would I write it in interval notation? This is with brackets and parentheses, remember? How do I write it in interval notation? Okay? Open bracket, 0, 3, close bracket. Now, before we go any further, I want you to see, it makes a lot more sense. This entire topic, and I don't know, some teachers don't ever do this. Take your calculator out real quick. It will make so much more sense if you do it this way now. Grab your calculator, please. If you forgot it for some reason, look on with the person next to you. Please use a graphing calculator. Don't use your iPad. Just slide over if you don't have it. Oh, you have it? Okay. Good. Go to Y1. Go to Y1. Type in the original function, y squared minus 3y. Forget that it's an inequality, please. Forget it's an inequality. Just graph the original. Y squared minus 3y. Oh, sorry. Use x. I apologize. Use x. Sorry. Yeah, I'm saying y equals, right? Yeah, no. Y equals x squared minus 3x. By the way, whenever you type anything in your calculator, in the functions, you always use x on the calculator. It's a placeholder. That's all it is. Obviously, it could be whatever variable you want it to be. Type in x squared minus 3x. That's what you should get. Hit zoom 6 if you don't get what I see. If you don't see what I saw on the top right there, take a look at what I just drew. If you're not seeing that, hit zoom 6. Zoom 6 makes your graph go from negative 10 to 10, negative 10 to 10 for your window settings. Yeah.
I'm sorry, what did you write? You guys
So you have it in Y1 yet or no?
yeah.
hit zoom.
Or no, I just don't want to put in
Oh, so in Y1, type in the original function, but use X. See the X button? It's like above apps. It should be above or next to apps. Is a key that says X there? It says XT theta N. It's right next to apps or math. So press X squared minus 3X. And then George hit zoom 6. You got it?
No, I accidentally pressed minus instead.
All right, so you're up in the next one. Let's make it clear. First of all, do you mind if I change settings? Do you use this often? I'm not going to class. I like class. I agree because that's what you're studying. So let's go back. Now type in X. So X is right there. Square. Nice.
See this recording.
X.
It's CV6.
Just good. All right. Now, here's what I want you to notice. When is this function below the x-axis? When is it below the x-axis? Look at it. From where to where?
In between 0 and 3.
And isn't what we were trying to do is to figure out when was this function less than or equal to 0? The x-axis is like your 0 line. When is the function above the x-axis? Everywhere else, right? And didn't we have positive signs here? So these signs indicate whether the function is above the x-axis, below the x-axis, above the x-axis. That's all it's saying. You see what I'm doing right now?
Yeah.
So whenever you solve an inequality and it says greater than or equal to or less than or equal to, all you're doing is searching for when it's above or below the axis. So when you take this test next week, you better be checking on your calculator. Check your work. You got to show me all your work algebraically, but you can check that your answer is correct just by graphing it. Do you all see that? Do you all see that your answers, 0 and 3 that you got from this equation, become the x-intercepts? Just like you had on the quiz. The second part of the quiz said find the zeros of the function. The zeros of the function, that was the term I used in that video you were to watch the very end of it over break. The zeros of a function are the x-intercepts. Okay? If you don't know how to find those x-intercepts yet, I'm going to did I put it on Moodle yet or I'm going to do it? There's a video about how to find x-intercepts in the graphing calculator. Instead of spending the time today to go over it, I'm going to put that video up, okay? So if you want to practice on how to find these x-intercepts, 0 and 3, to check that your answers are right, there's a way to do it on the calculator, besides just guessing by looking. All right? Okay. Let's go to the second one. Find and graph the solution of the following. Is this any different than the last one? Honestly. No, it's no different. Now you're looking for when is it above the x-axis, right? It says greater than. So you're looking for those positive regions now, but use the exact same approach as the previous problem. Exact same approach. I'm going to give you a head start, and then I'm going to try to catch up to you. George, come here for a quick second. So this works, for sure. I was telling Kate the same thing. This works. You can always break up the middle term and use grouping. But as soon as there's a 1 here, you don't have to actually do this extra step, because see how 4 and 3 were the middle terms? And see how 4 and 3 became those?
Yeah.
It's always going to be the case if there's a 1 in the front. Does that make sense?
Yeah.
So for this example here, what numbers multiply to give you -8 and add up to -2?
1 and 4. Or in 2 and 4.
2 and 4. And which is going to be positive, which is going to be negative?
The 4 is going to be positive and 2 is going to be negative.
Look at the overall.
Or negative 4.
Yeah, because you want the overall to be negative in the middle here. So as a result, the bigger number needs to be negative. And then the smaller number is positive. So instead of breaking it up and going an extra step with AC method, I would just go right to that, and then your answers are a little clearer.
Okay,
Does
yeah.
that make sense?
I had that on my sheet, on my iPad, and then, I had that now.
That's fine. Either way, it's fine. I just wanted to point out that AC method always works. That's the good part about it. But with problems where there's a 1 in the front, it's just an extra step or two, along the way. So even here, if I were looking at this one, you did fine with that. And this is good, actually. You're right. This is absolutely correct. But what comes out of here? What's in both of these?
X.
Yeah, and then if you take an X out front and put it here, what's left if you take the X out?
X and X. Or no, 2. Negative 2.
So this would become X
Equals
X plus 5, X minus 2, right?
Yeah.
That's where the 3 factors came from. So this works, the AC method, the way you did it. But if I were doing this problem, I would have seen that X was in all 3, taken that out first, and then gone unfactored.
Yeah.
Okay?
Thanks.
All right. I hope we got critical points at least by now. Once you do, go to your number line. Locate those on the number line. Open circle or closed circle? You should be able to tell right off the bat. Open or closed?
Open.
Open. How come?
Because it's not or equal to.
Good. This symbol here says greater than. Had it said greater than or equal to, we put a closed circle. So we could already put open circles at negative 2 and 4. And then all you got to do is test. Now, do you understand why I'm asking you to test in the factored form now? Do you see why it makes more sense? It's a little bit easier. So if I pick a number like 0 in the middle here, if I pick a number like 0, I don't care what this number is. 0 minus 4 is negative 4. All I care is that when I put a 0 in, this becomes negative. When I put a 0 in here, this becomes positive. Negative times a positive makes the middle region negative. The other regions will both be positives. And our goal is to ask the question, when is this expression greater than 0? Which pretty much means, when is this expression positive? We've got these two regions out here. So we've got from negative infinity to negative 2 and 4 to infinity. Okay, if I were to shade, I'd be shading here and shading here. In solution set form, we've got, x is less than negative 2 or x is greater than 4. The graph of this, you can tell me what it looks like already. Where are the x-intercepts? Don't use your calculator at all. Do not use your calculator. Where are the x-intercepts? Where are they? And negative 2 and 4. When is this function below the x-axis? Bridge?
Between negative 2.
Yeah, because Bridge noticed, hey, we got a negative here. This negative means it's below the x-axis. This means above. So this graph will be very similar to the previous slide or the previous example. Questions? So for those of you that have, in your previous math course, graphed parabolas, this is a very useful technique, evaluating the function by regions to know whether or not it opens up or down. There's another way we're going to be able to figure that out, and that has to do with what's called the leading coefficient, and we'll talk about that in chapters to come. All right, but this is a useful method. Any questions so far? All right, I want to see, I might let you just work with partners, because this is pretty redundant, right? After a while, it becomes similar. Example 3, let's do together, and then I'll let you work with partners on 4 and 5. Let's do 3 together. So example 3, the first thing I think about is this, and this is the key to example 3. It's really a repeated root. That's all it is. We talked about repeated roots in section 4.7. We called them double roots and triple roots. And the idea here is that when you solve this, what's your answer? It's 2 And it's 2, the same answer. So on your number line, here's your critical point. And we know it's a closed circle.
So that's where the vertex is of the parabola?
It turns out that it will be there, yes. It turns out that the vertex will be at 2. It's an interesting fact you picked up on. How'd you pick up on that? I'm curious.
Well, you said that if there's two things.
As they get closer and closer, the vertex is in the middle. Very good. See what he thought about? He picked up on that being the vertex. Because think about it. If your critical points were here and here, the graph might look like this, right? If they're here and here, the graph might look like this. And as they get closer and closer, the critical points get closer and closer, the graph gets narrower. Well, if the critical point is on itself, the graph's probably going to look like that. Okay, so Tristan's absolutely right. Okay, that turns out to be the vertex. Good intuition there. Now, we still need to test those regions, right? So if I test the point to the right of 2, I'll choose the point 3. Plug a 3 in, because I'm testing this region. Plug 3 in here and here. 3 minus 2 is positive. 3 minus 2 is positive. Positive times positive is indeed positive. Next, choose a point over here. Choose the number 1. 1 minus 2 is negative. 1 minus 2 is negative. Negative times negative, oh, what is that? It's still a positive. So when is this expression less than 0? Less than or equal to, really. But when is it less than 0, I'm asking you? Is it ever less than 0? No. It's positive here, it's positive here, and it's exactly 0 here. So if I were to graph this, as Tristan mentioned, that's where the x-intercept would be. This is what the function would look like. That's what it would look like in the top right. So the question again is, when is the function below the x-axis? When is the function less than 0? Is it ever down here? No, it's not. When is it exactly equal to 0? It's exactly equal to 0 at 2. Your answer is simply 2. Okay, be careful. You might want to say no solution here. But 2 works because this says less than or equal to 0. If it had just said less than 0, this would be an open circle and you would have no solution. Any questions on this at all? George?
Is this like another one of those things that you said you're only using for like the physics stuff?
You'll end up using this technique with testing regions and critical points in calculus, actually, as a senior. You will, for sure. Is it relatable in physics? Absolutely, but you'll use this actually in calculus. You'll directly use this in calculus, okay? I can't wait, because like when you're seniors, you're going to be like, oh, I remember Mr. Howell saying that, and it'll click. It'll click in your head. You will literally use what's called the number line test. It's called the first derivative number line test, but it's the same thing, with positive and negative regions indicating the graph itself. Okay, so this idea, correlating these two, is widely used. Try example 4 on your own. Maybe with the person next to you, you can check if you'd like to. If you need a hint, if you're having trouble, look up. If not, keep going. I wrote that in big letters because that should automatically pop out in your mind. As soon as you see this, that's the first thing you should think. Then you should think this. After GCF, you should be thinking dots. You don't have to call it that, but you know what I mean by that, right? Difference of 2 squares. Oops. What does w squared minus 16 become? Annette?
W plus 4, W minus 4.
Good. Okay, if that didn't ring a bell in your head, you got to go back and look at your stuff, right? You got to practice still. And remember that when you have a difference and they're both squares, you can write them as the difference of squares. Don't let the number line confuse you, please. You might have an extra region. It just means you have to test an extra point. I got 3 boundaries now, right? 3 boundaries, and therefore 4 regions. If you ever forget that, by the way, think about like a candy bar. If you make 1 cut in a candy bar, how many regions do you get? 2. As many cuts as you make, you get 1 more region always, right? Or piece of the candy bar. And again, test the points in the factored form right here, please. So when you go ahead and test like the number 5 out here, please test it here. 5 becomes positive, a 5 here becomes positive, a 5 here becomes positive. Positive times positive is a positive. If you're done, try and draw the graph without actually looking at your calculator. Try to fill in the blue graph at the right of what this curve should look like without using your calculator. Use your intuition instead. Check your regions. If you have the same regions as me, please. I have alternating regions here. If you didn't get the same, then maybe go back and test another point and check. I would test points like 5, 1, -1, and -5. I always test the points closest to the boundaries. Any integers closest to the boundaries. This graph, or this original function, wanted to be greater than or equal to 0, which is positive. So I'm going to shade the positive regions. So my solution set is from -4 through W up until 0, or W greater than or equal to 4. Look at my solution set, please. Make sure yours looks the same. You've got a region and then another region, so you have an OR statement in between. If I were to do this with solution set, with interval notation, it would be -4 to 0, or 4 all the way to infinity.
When you make like the sections, are they always going to be like
alternating?
Yeah.
No. Right now, yes. Almost all of these examples are alternating, and your homeworks, a lot of them are too. But they will not always be, actually. So you do have to test. It becomes with a quadratic, you're going to get like positive, positive, negative, or negative, negative, positive. It really will always be. Or that example with the 2 where it was the vertex that Tristan pointed out. So you can get that. But with higher order polynomials, it won't always alternate. It won't always. You get like weird looking shapes. Just wait till you get to calculus. You get like, so let me draw this graph and then I'll show you one that doesn't, okay? What would this graph look like? Anybody have an idea? What do you got? It would look like this, right? What do you got? So where is it negative? Where is the region negative? It's negative down here, right?
Yeah.
Everybody sees that? And then from 0 to 4, isn't it negative also?
Yeah.
From 0 to 4, it's negative. See what I just did? Everybody see what I just did? I filled in the negative regions for my number line. And then look at the number line. Since from -4 to 0, this region is positive, this region is positive. Since this is positive, this is positive. So it turns out that this is what it would look like.
It's like a squiggly line.
Yeah, it's a cubic function. A cubic function generally looks like this. That's the general shape of a cubic at the top. Okay? So again, This region is above the x-axis. This is above. These are positives. This region is below. This is below. These are negatives. Okay, I'm literally showing you like a lot of calculus right now, believe it or not. Curve sketching in calculus is huge, and this is one of the techniques you're going to learn later on. Now, George, to answer your question, George said, are they always going to alternate? A graph could, believe it or not, have what's called a corner or a cusp in the graph, and a cusp would look like this. So for example, here, this would be a critical point, but if you test it on the number line, you'd get negative, negative, positive, negative, positive. So you can have a double sign repeated when you have like what's called a cusp or a corner. It's a weird shape, but it is actually very common that it occurs. You don't see it in your algebra and your like early courses because it's a lot more complicated to understand, but you're going to see that in your calculus course. Okay? So it won't always alternate. In this class though, you're going to see them almost always alternating. The last one looks difficult, doesn't it? It's not that bad actually though. It really isn't that bad. But you need to remember that you got to get everything on one side of the equation. Okay, the first step is to move everything to one side of the equation. So let's do that. I'm going to distribute the h squared to both terms first. I'm going to move the 6h cubed over. I'm going to factor out h squared. And then I'm going to write down h minus 3, h minus 3. Okay, this becomes a weird one only because you get a double root twice. Your critical points are 3 and 0, but these are both double roots. These are both double roots in the end. Okay, you'll get a weird looking graph. You got 0 and 3 there. It turns out these will be open circles and everything will be shaded actually. They will all be positive, positive, positive. George, this is one of those weird looking graphs we're talking about, okay? So you'll end up getting all real numbers except for 0 and 3. If you want to look at that a little bit further, please look at this example in the video. Hey, your homework for this second, for the first time this year, part of it is out of the oral exercises. It's the first time I've done that all year. I wanted to point that out. So when you do the homework, you do 1 through 6 of the oral exercises, then jump to the written exercises. Okay? Tomorrow we have 5-1 and 5-2. Friday problem sets are due. Monday is test. Keep this in the back of your mind. Office hours today after school if you want to come by.
I'm going to come by a little